Okay, so today I'm going to be finishing up coverage of iterative methods for AX equals B. So the last section was all about AX equals B for a case of A being symmetric positive definite. So steepest descent, Lanczos, and then conjugate gradient. So the purpose of today's purpose for today is to try to, in some sense, generalize the ideas behind conjugate gradient to obtain some kind of iterative methods for solving AX equals B, where A is a more general matrix, still square and invertible, but not even necessarily symmetric, let alone positive definite. And the idea of it came about from the symmetric positive definite case that led to conjugate gradient. It's the notion of a Krylov subspace, where you start with a certain vector, like you have a right-hand side, or B, or the initial residual, and keep multiplying it by A to generate a subspace that's called a Krylov subspace. So that notion of Krylov subspace we're still going to use today. So we're going to see members of a family of methods called Krylov subspace methods for X equals B. Right. So the first type of method we'll see is the kind of method called a minimum residual method. And we're going to see two such methods, one for the symmetric case and one for general invertible A. So the idea is we assume that the solution has a certain form, which is a form we've seen already, and try to and the goal is, given a solution of that form, try to make a residual, B minus AX, as small as possible. Okay. So to recap, we've seen this notion of a Krylov subspace before, so we're going to use that again today. So we take our initial residual, which is B minus A times our initial guess, which might often be the zero vector, and just keep multiplying by A. You may recall that the Lanczos iteration computed an orthonormal basis for this Krylov subspace. So that's going to be done again today. Right. Now, so what we saw when we had the Lanczos algorithm, we had iterates, so approximate solutions of AX equals B, that were of this form. Now, it says here conjugate gradient generated these approximate solutions. Now, even though conjugate gradient did not compute this explicitly, Lanczos did, but Lanczos and conjugate gradient generated the same iterates. They just did so differently. In conjugate gradient's case, it was much more efficient. Right. So, so we're still going to assume a solution of this form, and see what we can do in the case where A is not symmetric positive definite. Okay. Now, just as in the case of Lanczos, as I mentioned, we want to generate this matrix QK that consists of columns that form an orthonormal basis for this Krylov subspace. Okay. Now, the way that was done before in Lanczos was we generated a sequence of orthogonal polynomials. Because orthogonal polynomials satisfy a three-term recurrence relation, so we could have each new orthonormal vector obtained only from a previous two. Now, to do that, you need an appropriate notion of an inner product of polynomials. And this was the inner product that we used for the Lanczos algorithm. So if f and g are functions, in this case, is polynomials we were interested in, the inner product would be defined this way, with functions f and g applied to the matrix A. The problem is we can't do this in the case where A is not symmetric positive definite, because then an inner product defined this way is not actually a valid inner product. One of the key properties of an inner product is that the inner product of a vector, in this case a function, with itself needs to be a non-negative real number, and it can only be 0 if the function itself is 0. And that doesn't happen if A is not symmetric positive definite. So this idea of generating a free-term recurrence relation that defines orthogonal polynomials is a non-starter in this case. But we're not out of luck. We already are aware of an orthogonalization process that we've used before, and that is Gram-Schmidt orthogonalization. So we previously saw Gram-Schmidt as a way of computing the QR factorization of a matrix. So you're given a set of non-orthogonal vectors, you have columns of A, and this process would orthogonalize them. So we can use that here. So to explain how it works, let's assume, so think in terms of an inductive argument. Suppose we've generated a sequence of orthonormal vectors up to this point, q1, q2 up to qk. Then all I would need to do is describe how would we compute qk plus 1 from these. So what you do is, all right, so the goal is now to compute qk plus 1. That's a member of this Krylov subspace, but is orthogonal to the previous ones. So keep in mind, if B is the initial vector in your Krylov subspace, actually, I need to fix this. Yeah, I'm going to make, to be more precise, it's not necessarily B. It would be R1, which is the initial residual, which is B if the initial guess is 0, but we don't necessarily want to assume that. So I'll just edit this real quick. Okay. So the Krylov subspace spanned by these vectors, q1 up to qk, consists of all polynomials of A of degree up to k minus 1 times the initial vector, R1. So this new subspace would consist of all polynomials of A of degree up to k applied to R1. So if qk comes from a polynomial of degree at most k minus 1, I multiply it by A. Now we have a polynomial of degree k, or at most k, applied to R1. So this vector does belong to this Krylov subspace. All of these vectors do. So I have a set of vectors that spans a subspace. It's just that these vectors are orthonormal. This is not orthogonal to the other ones. That's where Gram-Schmidt comes in. So what I do is I subtract from AQK the projection of AQK onto all of my previous orthonormal directions. So QJ transpose times this vector projects AQK onto the one-dimensional subspace spanned by QJ. And those subspaces come from vectors that are orthogonal to each other. So I just subtract each one of these projections off. That's what Gram-Schmidt does. This is exactly Gram-Schmidt. And now I have a vector VK that is orthogonal to all of the previous Qs, Q1, Q2, up to Qk. So if this is heading in a direction that I want, I just need to normalize it, which I do here, and now I have Qk plus 1. So that's how I generate each new vector in my orthonormal set. And here, all I'm doing is confirming that if I take any of the previous Qs, Q1 up to Qk, and take the inner product with Vk, and I just work out the algebra here, these Qs are orthonormal, so this inner product here is 0 unless j is equal to I, in which case it's 1. So this becomes 1, and everything cancels, and we get 0. Okay. So sure enough, these vectors really are orthonormal. So the first vector in the Krylov subspace Q1, you could obtain that just by taking your initial vector, R1 in this case, just normalize that. That's how you start the process. And then each new vector after that, Q2, Q3, and so on, is generated using this. Now, each new vector takes more work to generate because this summation is going to have more terms. So that part is unfortunate. But at least we have a way to generate an orthonormal basis for a Krylov subspace. It's just not as efficient as in the symmetric positive definite case. Okay, and this I mentioned how you generate the initial vector. Now, if you look here at how these vectors were generated, we see these quantities throughout. So Qj transpose A Qk for various, and the indices, J is always less than or equal to K in this case. So if I go ahead and define a matrix H using its formula, so this right here would be HJK. And then, and this is this is for I is less than or equal to J. And then I define this matrix entry, so Hj plus 1j, to be the 2 norm of this new orthogonal but unnormalized vector that I generate here. Then, if I return to what I had before, this is your orthogonalization process again, just using different indices. And I replace this with Hij that I've defined here. Then just rearrange a little bit. But then Vj, I want to normalize to get Qj plus 1. So Vj is now replaced by this. But Vj is Hj plus 1j. So I can, so now by filling that in here, I now have this. So I can express A times any of these Qs in terms of all of my Qs that I have, including the next one. So now I'll take each of these and slap them together into a matrix. So now I have my matrix matrix capital QK that consists of Q1, Q2 up to QK. So capital QK is a matrix of orthonormal columns. And what I have right here is I'm taking a linear combination of these Qs. That gives me each column of this expression. This is a matrix vector product. In fact, if I broke down these entries, okay, yeah. So, and if I wrote Qi in terms of its entries, I'd actually have what's a matrix product. Each column of this is one of these summations here. And then I have, in the case of j equal to k, I have little q k plus 1 here. But what's happening right here is this matrix product involves only the q1, q2 up to qk, not qk plus 1. So this term has to be written separately out here. And the multiplication by ek transpose, this is a vector that is all zeros except for a 1 in the k position, and it's a row vector but because of a transpose. So this right here is a matrix that is entirely 0 except this quantity right here, this scaled vector, sits in the last column, the kth column. Because keep in mind, this is n by k. This is n by k. And so everything here is n by k. All right. So now I can express AQK in terms of QK times a smaller matrix HK. This is only K by K. But another way to write it is I can take this whole thing and represent it as one matrix product involving QK plus 1. That consists of Q1, Q2, up to QK plus 1 times this matrix HK tilde. Now, what do these matrices look like? Here's HK. It's almost upper triangular. It's just that it has this one diagonal of non-zero entries that sits immediately below the diagonal. And then HK tilde is the same matrix, but with a row tacked onto it that is all zeros except for this one entry, HK plus 1K, that sits in the kth column. All right, so when you have a matrix that is 0 from the second subdiagonal all the way down to the lower left, that's an upper Hessenberg matrix. And we'll be seeing more of these. Upper Hessenberg matrices will play a key role in the next chapter when we deal with methods for computing eigenvalues. Okay. All right. So for our one live attendee, so I want to check if Dale, if you have any questions up to this point.
I've been trying to picture right at the top of your screen, the second line of your screen. It looks to me like your HJ plus 1, JQJ plus 1 is just updating the last column of AQJ. No.
Oh, okay. So
I'm down a little farther. I'm down in equation.
Oh, this.
Yeah.
Yeah. Okay. And so what's happening is, yeah, but this is only affecting the last column. And so suppose we look at an earlier column. Like here, if I look at the first column of this, that's AQ1. AQ1 would be a linear combination of Q1 and Q2 that's accounted for by these two entries here. AQ2 would be a linear combination of Q1, Q2, and Q3. Each of those would be multiplied by these elements here. So A times any of these Qs can be expressed as a linear combination of Q1 and Q2 up to the next Q. But in all of these cases, except for the last one, this next vector can be accounted for in this matrix product. Because here we have any linear combinations of Q1, Q2 up to Qk. It's only when we get to the last column that, because we have this, like AQK is going to involve QK plus 1, there's no way to account for this contribution to AQK in here. Because this is taking linear combinations only of Q1 up to Qk. So that's why it's written separately.
Thank you.
And then if we're okay with having a slightly non-square matrix here, then we can account for everything in just one product. Okay. So we have a way of generating an orthonormal basis for a Krylov subspace, and we can see how so we have a way of expressing what happens when we multiply A by those vectors in terms of the vectors themselves. So that's convenient. Okay. Okay, and then just some general reminders. But to give you an idea of what happened here. That anytime you're taking a linear combination of vectors, you can think of it as a matrix vector product where the coefficients in linear combination are forms of vector. The column vectors that you're taking a linear combination of form a matrix. So you can always use that perspective. That sometimes can make certain other things easier to see. And then if I have a bunch of matrix vector products like that, in other words, like this AQ1, AQ2, etc., and I stack them horizontally like this, then I can think of that as a matrix-matrix product, where the matrix here consists of all of these column vectors that are being multiplied by A. A lot of times when you have everything written out at the element by element level, like I have here, it can be difficult to see what's going on. But if you can think of it as viewed in terms of operations on matrices as opposed to vectors and scalars, then some things can be easier to see that way. And just as an example, if I have this is a case of j equal 2 or 3, if I write out these linear combinations of the q's and the coefficients in linear combination are these elements of a matrix, capital H, then I have this going on here. So then if I take this linear combination for the j equal 2 case and this linear combination for the j equals 3 case, and I put them next to each other in a matrix, because we're taking linear combinations of the same vectors, the q's, I could write this as a matrix product where I just put these two columns together in this matrix. And because of this linear combination does not involve Q3, only Q1 and Q2, that's why I would have a 0 here, because this coefficient is multiplying Q3. So this hopefully helps you see how I get the matrix perspective on on what's happening here as we generate these orthonormal vectors. So now that we have a way of getting this matrix, how do we get our approximate solution to AX equals B? Now, the goal before that led to Lantos iteration was to make each residual orthogonal to all previous residuals. We're using a different criterion now. We just want the norm of residual, given that the solution must be of its form, we want to make a norm of residual as small as possible. So that's what unfolds here. So here's going to be our residual from this, whatever we end up computing, because we don't have this vector yk yet. That's the focus now, is how to get this. So we write out what the residual is, and then xk I write using this form. So now I have the initial residual here, which was previously labeled as V0. It also happens to be R1, but V0 is what I happen to be using here. But V0 is a multiple of Q1, my first orthonormal vector. And then AQK was previously worked out to be equal to this, QK plus 1 HK tilde. Now, from this point, I use the fact that the 2 norm of a vector is invariant under multiplication by a matrix of orthonormal columns. So I can multiply this whole expression by QK plus 1 transpose, and that'll have the same 2 norm. Okay. Now, okay. So we have this cancellation here. And if I label the 2 norm of V0 to be H10, just for consistency with how other subdiagonal H's are defined, then I have this expression. And I want this to be as small as possible. But what I have here, HK tilde is a matrix that has K plus 1 rows and K columns. So what I'm actually solving here is a full rank least squares problem. So what we saw at the beginning of chapter 4. So we already know how to solve this problem. You can use normal equations, or you can use a QR factorization of HK tilde using any of the approaches that were covered back then. So now we have a way to solve for YK to make the residual, this residual, as small as possible across all solutions that are of this form. So now, okay. Sorry, there's one sticking point that I need to address here. Okay. Actually, I need to check on how much of it's played out in the text. Oh, okay. It actually had more steps laid out here. Now, keep in mind, capital QK plus 1, that is a rectangular matrix. It has many more rows than more rows and columns. Now, for a matrix like that, I can say that QK plus 1 transpose QK plus 1 is identity. But the other way around, QK plus 1 transpose, so the second matrix being transposed in that is not identity. That is a projection. So one thing that I need to be careful about is in making sure that this norm is equal to this one. What I really should have is not QK plus 1, but if I extended this orthonormal basis described by this matrix into an orthonormal basis for the full space, then I could have that matrix here, and that would that kind of matrix would satisfy, like, QQ transpose is identity, and then I could be sure that the norms are equal. The reason why I don't have an issue here, why I can still say, even though I'm glossing over the fact that for this matrix, QK plus 1 transpose is not identity. The vector that we have here is already belongs to the range of QK plus 1. So that's why I can correctly state that this 2 norm is equal to this 2 norm. So if this was an arbitrary vector in Rn, I could not say that these 2 norms are equal. But since this vector is already known to be in a range of qk plus 1, I can make that statement. Okay. So all the pieces of the algorithm are now in place because we're trying to compute solutions of this form with each iteration. We now know how to get this matrix. We also know how to get this vector by solving this full-rank least squares problem. So putting it all together, we have what's called GMRes, the generalized minimum residual method. So this is one of the most popular iterative methods for solving AX equals B in the general square invertible case where there's no symmetry. Okay. All right. So you first choose initial guess, which you can always choose to be 0 if you don't have any particular initial guess in mind. We have our initial residual, and then this scaling factor will be needed for the least squares problem that we solve. And now we kick off the iteration, where these steps here and this loop here, all these steps here, their purpose is to generate each new vector in the orthonormal set of Krylov subspace vectors. So these form the columns of the matrix capital QJ. Now keep in mind, it is a while loop, so J is only incremented because I have this statement here, J equals J plus 1. But what that means is what's known as QJ plus 1 right here now becomes known as QJ down here because this increment happens in between. This is the Gram-Schmidt part. And then in the process, I obtain the entries of my Hessenberg matrix, HJ tilde. And once I have updated my orthonormal basis and my Hessenberg matrix, then I have everything I need to solve this full rank least squares problem by whichever approach, normal equations or QR, to get my vector yj. And now I have my new iterate. Yeah. All right. So this is our first attempt to do something conjugate gradient-like for the case of A not being symmetric positive definite. Okay, now, so I should mention that the iteration that produces these Qs, that's called Arnoldi iteration. You can think of Arnoldi iteration as a generalization of Lanczos iteration to the non-symmetric, case of a non-symmetric A. Now, what if A is symmetric? This is the same relationship that was given earlier for Arnoldi, but the only difference is I've labeled this as beta k. That was previously labeled as hk plus 1k. Now, if I multiply both sides of this equation by qk transpose, then this term would just reduce to hk. This term would go away because capital QK has columns that are orthogonal to QK plus 1. So I end up with this. And I can also get that HK transpose is equal to this, same expression, except we have a transpose here. But what happens in that case is if A is symmetric, so A equals A transpose, then HK has to be symmetric as well. But when a matrix is upper Hessenberg and symmetric, it ends up being a tridiagonal matrix. So I'm going to refer to that as TK going forward. And it turns out it's not just any tridiagonal matrix, it's the same tridiagonal matrix that Lanczos generates. In other words, Arnoldi iteration, when asymmetric, just reduces to Lanczos iteration. Okay. Because either way, you're getting an orthonormal basis for Krylov subspace. I just realized something notation-wise. In terms of how I write Krylov subspaces. Ah, dang it. Okay. Sorry, this notation's a little inconsistent. Normally, when I've been describing Krylov subspaces, I put the vector first. Here I put the matrix first for some reason. Okay. So what happens is, if we want to adapt this approach to a symmetric case, we can perform Lanczos iteration, as described previously, to compute this tridiagonal matrix. And although you'd have one extra row where you have your subdiagonal entry sitting by itself in the last row, just like what I just described for forming HK tilde from HK. So it's not exactly the same as the Lanczos algorithm for AX equals B described in the last section. It's almost the same. The only difference is to get this vector YK, we're solving this full rank least squares problem, similar to the one in GMRes, where this is a K plus 1 by K matrix. You may remember from the last section, to get this vector YK, we solved a square system of linear equations involving just TK, not TK tilde. So that was done to make sure all the residuals were orthogonal. Now we don't care about that. We're just trying to make the residuals as small as possible of each iteration. So then we solve this least squares problem instead. So this is called minres. So this is the minimum residual method for only for symmetric matrices. So that's where GMRes gets its name. Um, I I don't know offhand, but I'm guessing just by the naming convention that minres was probably developed first, and then for to handle a symmetric case, and then it was generalized to the non-symmetric case by replacing Lanczos iteration with Arnoldi iteration, and working with a Hessenberg matrix instead of a tridiagonal matrix, and that was called the generalized minimum residual method. It's just that once you go for all the trouble explaining GMRes, MinRes falls out pretty easily just from how it simplifies so much when you assume that A is symmetric. So I have to make a note of this yet another mistake I just found in notation. Okay. Any questions up to this point? Okay. Well, could we just now look at the chat? Okay. Now, one key aspect of a symmetry is, in the case of minres of A being symmetric, each new vector in your orthonormal basis, qk plus 1, depends only on the previous two. Whereas in GMRes, it depends on all the previous ones. So that means that GMRes has a lot more work to do. The amount of work needed to compute each new Q vector is um, is growing from one iteration to the next. Whereas in MinRes, that's not true. It's the amount of work per iteration in terms of generating vectors is the same. However, in both methods, you're solving a least squares problem with a larger matrix. So that amount of work is growing too. So that's one significant drawback of both MinRes and GMRes um, compared to, for instance, conjugate gradient, where in conjugate gradient, the amount of work per iteration is exactly the same. Yeah. Okay. Um, Now for although I actually want to check something about this. Oh, okay. I There's one detail I forgot here. Um, MinRes, as I've described it, this system takes more work for each iteration. However, with a bit of algebra, which I won't get into here, it is possible to um, compute each new iterate. Because notice here, for both MinRes and GMRes, as I've described them, xj is in terms of the initial guess plus this linear combination of Krylov subspace basis vectors. But it is possible in the MinRes case, not in GMRes, but for MinRes, it is possible to rework this so that xj depends on xj minus 1 plus some term. So just like just a conjugate gradient is able to generate each new iterate efficiently from a previous one. I haven't shown you how to do that in MinRes, but I can tell you that it is possible. And that's actually in an exploration that I had some mercy in not assigning. Um, so that was by Page and Saunders. I actually know um, uh, uh, both Page and Saunders. Saunders is at Michael Saunders is at Stanford. Um, I guess actually he's my academic brother. Um, okay. Um, all right. So while MinRes with some work can be made so that's like conjugate gradient, pretty much the same amount of work per iteration, GMRes cannot. Um, so what is often done in practice with GMRes is occasionally the iteration is restarted. So whatever um, approximation you got so far for x, your solution of x equals b, use that as a new initial guess and restart the iteration. So that way, the size of your Krylov subspace basis and therefore the size of your Hessenberg matrix is bounded, at least. Um, so these methods are implemented in MATLAB. So there are functions, GMRes and MinRes. So one of the parameters you can specify for MATLAB's GMRes is after how many iterations would you like the iteration restarted? Okay. Now, here's a whole other approach to trying to extend conjugate gradient to more general um, matrices. Because we like to generalize in such a way that, like a conjugate gradient itself, each iteration has about the same amount of computational expense. Um, so what we'd like to do is generate basis for Krylov subspace using what's called a short recurrence relation, where, for example, in Lanczos iteration for symmetric matrices, you have each new orthonormal vector is obtained only from a previous two. Um, so how can we do that in a case of A not being symmetric? Yeah, the answer is you give up orthogonality. So we're no longer going to require that these this set of vectors that's generated efficiently forms an orthonormal set. Instead, we build two Krylov subspaces. So we've generated initial residual like before. This is exactly the same as it was. But then also a similar vector involving A transpose. So now we have these initial vectors, two of them, R1 and R1 hat. And from them, we generate two Krylov subspaces, one using A and one using A transpose. And instead of generating one Krylov subspace where the vectors, the basis for it is orthonormal, instead, we have these bases be bi-orthogonal. And what I mean by that is, for this Krylov subspace, we generate vectors Q1, Q2, and so forth. And then for this Krylov subspace, we put hats and everything, Q1 hat, Q2 hat, etc. And whereas before we wanted Qi transpose Qj to equal 0, if I is not equal to j, now we have this. Notice this Qi hat transpose Qj is the Kronecker delta Ij. In other words, 0 if I is not equal to j, and 1 if they are equal. So here's another way of looking at it. I form a matrix capital QK as before, with these vectors as columns. And then I have defined QK hat in a similar manner from the vectors QJ hat. And then they'll satisfy this relationship. So what that means is I can describe each of these vectors as a polynomial of A times the initial vector of a Krylov subspace. And if it's a vector Qj, then that polynomial will be of degree at most j minus 1. And we're using polynomials of A for this Krylov subspace, and then polynomials of A transpose for this one, and different polynomials in each case. So now, if I want to generate these vectors using a process similar to Gram-Schmidt orthogonalization, it's just that now I get the entries of this matrix by multiplying by Qi hat transpose instead of Qi transpose. So it's not exactly Gram-Schmidt. It just, again, it has that framework. So, um, so I want to choose. So this is how I choose Hij to make sure that I have bi-orthogonality of these two sets of vectors. And this choice of Hij does in fact ensure that, because if I multiply both sides of this equation by Q, wait a minute, make sure I have this right. Hold on a second. Yeah, that's right. Um, Hold on, I'm going to cheat a little bit. I want to make sure I'm not telling you the wrong thing. Um, So then I have K. Sorry, just making sure that this is correct. It is. Okay. All right. So by making these vectors biorthogonal, that has the effect of making these polynomials of A and A transpose what are called formally orthogonal. Now, the difference between formally orthogonal polynomials versus just plain orthogonal polynomials is that formally orthogonal is with respect to an inner product that's not actually a valid inner product. So this is the inner product in question, where okay, that I've defined right here. We have R1 here and R1 at transpose here, and A is a general square invertible matrix. And because A is not symmetric positive definite, this would not satisfy all the properties of a valid inner product. For example, making sure that the inner product of any function, any vector or function with itself is a non-negative real number. That's not guaranteed here. All right. All right. Now, if I look at this matrix entry where I is strictly less than j minus 1, then what happens is I replace this with its definition in terms of polynomials of A or A transpose. And in terms of this inner product, I end up with, because of this factor of A right here, I end up getting this formal inner product of a polynomial degree j minus 1 and a polynomial of degree I minus 1. And what happens here is this polynomial of lambda is of degree I because of this lambda sitting here. And this is a polynomial degree j minus 1. But if I is less than j minus 1, these polynomials are formally orthogonal, and therefore this inner product must be 0. So what that tells me is this matrix H defined in terms of these inner products is actually a tridiagonal matrix. So we have a 3-term recurrence relation, just like Lanczos iteration, where each new vector in each of my biorthogonal sets can be computed using only the previous 2. So here are the recurrence relations that we get. So from each new Q to these previous 2 Q vectors, I get the next Q vector, and the same for the Q hat vectors, just using the transpose. So this is exactly the same kind of recurrence relation we saw in the Lanczos algorithm, and then again here just with different constants and A transpose instead of A. So now we have an efficient way of generating these 2 biorthogonal sets of vectors. So this works for formally orthogonal polynomials just as well as for truly orthogonal polynomials. So from these 2 recurrence relations, we get these kind of relationships here. Because what I could do is I could use this equation, for instance, to write A times Qj as a linear combination of Qj minus 1, Qj, and Qj plus 1. So that means that A times all of these Q vectors would be equal to all those Q vectors times a tridiagonal matrix that comes from having the alphas on the diagonal, the betas on the subdiagonal, and the gammas on the superdiagonal. And then we have this one term left over, like we saw before with GM res. So now I have this matrix that's not symmetric, being formed in terms of capital QK and capital QK hat. Okay. So this process I've just described is called unsymmetric Lanczos iteration. So it requires two initial vectors, generates biorthogonal, two sets of vectors that are biorthogonal, still generates a tridiagonal matrix. It's just not symmetric because A is not symmetric. So this is the full unsymmetric Lanczos algorithm. Oh, that should be bold. Whoops. Okay. Okay. Sorry. Yeah, never a mistake to make a note of. Um, all right. So this just summarizes what was done earlier to generate these biorthogonal sets of vectors. And also the tridiagonal, unsymmetric tridiagonal matrix that relates them. So I have a constants alpha k. And this is a rather unusual way of describing gamma k times beta k because we don't have a formula for gamma k or beta k individually. All we have is that the product must be equal to this inner product of these vectors. Other than that, you can specify gamma k and beta k however you like. For example, what you could do is say that beta k would be for example, the one convention is the square root of the absolute value of this number. Um, and then gamma k would be equal to this quantity divided by beta k, just to make sure that this holds. Um, and then that way gamma k and beta k would be plus or minus each other. But that's just one convention. Okay, yeah, so that's what I meant here, that there's some flexibility here. Oh, yep, that's exactly what I mentioned. Okay, now one big problem with unsymmetric Lanczos that is not an issue with regular Lanczos is suppose these vectors are non-zero, but they're orthogonal. That's what's called serious breakdown. We definitely don't want that to happen. Um, and so then you don't even get a decent approximate solution. Um, that's actually a welcome event in Lanczos iteration where uh, actually what could happen is that this vector itself is zero. We actually like that because then you have what's called an invariant subspace and you can compute the exact solution. But when this happens, you're toast. All right. So what's done here is this process using unsymmetric Lanczos generates solutions that are once again of this form. And now, instead of having all the residuals orthogonal, what we have is each of these residuals is orthogonal to, so instead of being orthogonal to each other, they're orthogonal to all columns of the other matrix, so QK hat. We have the same tridiagonal system to solve as before. Um, it's just that now TK is not symmetric, but it's still tridiagonal, so that can be solved efficiently. Um, but just as how we change Land trails to get conjugate gradient, we'd rather have each iterate defined in terms of a previous x, not the initial x. So a lot of work is done that I won't go through here to get the final algorithm, which is by conjugate gradient method. And if you compare this to regular conjugate gradient, you see it's quite similar. It's just that it's doing a lot of things twice, like finding new search directions, two sets of search directions, two sets of residuals, one involving A and the other involving A transpose. So unfortunately, this algorithm involves two matrix vector multiplications in each iteration. So right off the bat, has twice the overhead of regular conjugate gradient. So this is another way to generalize conjugate gradient to the unsymmetric case. You're just doing all these things for A and its transpose. But this algorithm that I've shown you is numerically unstable. And you can use preconditioning with it, like you can of conjugate gradient, but it's still numerically unstable. So fortunately, the algorithm's been modified to obtain what's called BiCG stab. So that deals with the numerical instability. I should mention this is a site that I've had some of my students use in the past for research. It has a collection of matrices that are very good for testing iterative methods. There's all kinds of like large sparse matrices and so forth. And it even provides code in different languages to help you work with these matrices. Okay. Oh, I've come to the end. Yep, I really have come to the end. Okay, so all right. So that's how we can attempt to have a conjugate gradient-like method for more general matrices. The methods involved have their issues, unfortunately. They're not great. Um, but um, it's it's a step. So, but these kind of iterative methods, and preconditioners for them is still a very active area of research. Okay. There's still some time. Are there any questions about this or homework problems? Oh, geez. And I know a feeling. Um, okay. All right. Well, that brings this chapter to a close. On Thursday, I'll start the last chapter that I'll be covering from my book, chapter 6. That's on methods for computing eigenvalues. But some of the things that we've seen already will play a key role, such as QR factorization, given householder matrices, just used for a different purpose. It's actually my favorite topic of this class. But we'll see if you all agree. All right. So hope you feel better, and I will see, well, somebody in some sense on Thursday.